Good morning. Hi, Chris.
Morning. How are you?
Good.
Good.
Quite a bit different weather from today than yesterday.
It's very different.
Yesterday it was, well, warm compared to, the winter we've been through. And then suddenly today cold again.
Yeah, this weekend was pretty nice weather.
Yeah, it was. Let's see, it's just you on Zoom, and we got at least one or two people on YouTube. Well, this is week 13, I believe, of the semester. So we have this week 13, and then we've got 14, 15, and 16. So there's 3.5, 4 weeks left of the semester. And so, what are we going to do over these next few weeks? Let's see if we can kind of outline roughly what we're going to be doing. Let me get my iPad up and running.
Yep.
Okay, so this is today here, week 13, then we have week 14, week 15, and week 16. Now, week 16 is already kind of set aside for, well, I don't have a final in this class, but I am going to meet with each one of you for about 5 minutes on Zoom, and we'll go over all of the work that you've done over the semester and arrive at a consensus about what your grade ought to be. So that'll be basically the entire week. So starting on week 15, I will put up some time, a spreadsheet where you can fill in like where you want to do your meeting. I'll have a whole bunch of time slots available, and you just fill your name in for the one you want to do. So That'll be the entire week of 16. So what are we going to do between now and week 16? So week 13, we are introduce the final password cracking program. And we'll start in on networking. And then I think week 14 is when we'll finish with networking. And in fact, I'm not sure when we'll introduce the very last programming assignment we're going to do. It's either going to be here at the end of week 13, so in other words on Thursday, or we're going to do it maybe over here Tuesday of week 14. But then you can see that we've got 1, 2, 3 slots here that kind of don't have any real topics for them. So I was thinking we might do, well, these days I do maybe one class session on quantum computing. And so a little bit of an introduction to quantum computing, and then how we can simulate a quantum computer in a traditional programming language like C. We'll actually write some code to simulate one. And I'm not saying that this will happen on week 15. I'm just saying, like, here's some stuff to happen in this blank slots here. Another popular topic is I break out one of my old computers that I got back here and show you maybe what it was like to develop code on one of those things. And we can also do Q&A sessions for any last programming assignments that you need to wrap up. And who knows, maybe there's something else we can throw in there. We'll figure it out. Hold on a sec. So that's a rough outline for the rest of the semester. Does it look good? I mean, I can't believe we're like already almost there. We're 3/4 of the way through the semester. And then starting in the fall, in late August, we'll do it all over again. So I'll get a new batch of students who, you know, have never really seen C before, and you know, learn all the basics and go back to, well, I mean, can you believe that it was only 12 weeks ago when you know, you were trying to figure out how to draw flags. And how to draw pictures of barbecue grills. So, you've come a long way since then. So let's take a look at this last programming assignment, not the last one, the second to last one, but the last one having to do with cracking passwords. So, I don't think I brought this up before, but there's this term called a rainbow table, and it basically means a table in which you have taken all of the potential candidate passwords and pre-hashed them and stored all of those into some kind of data structure. A rainbow table is something more specific, but this is good enough of a definition to basically mean it's a lookup table of pre-hashed passwords. So what you're going to do is log into Bitbucket, and you're going to fork my crack3 repository. So those of you who are on YouTube and want to give this a try, here is the address. No, it's not quite good enough. The address is basically this, what I've highlighted. And I can go ahead and type that into the chat. My voice is terrible today. And the repository comes with starter files. It comes with a make file. And I think this one is all ready to go. Yep, there's nothing you have to do to this one. Comes with a starter crack.c file. And in a moment, we'll take a look at that. Comes with a working hash pass. This is very similar to the program that you wrote a couple of weeks ago. And then some of the auxiliary programs you need, like md5.c, md5.h, and some rocku files. So there's 3 that I've given you, and there's actually one more that can be downloaded and put into your environment. It's so big that I didn't want to put it into Bitbucket, but there is a makefile target for downloading that file and then putting it in. It contains 3 million entries out of the Rocky file, which should be just big enough, I think, to fit in to the memory that our system has. Okay, so let's take a look at crack.c. Actually, let me just clone this into my environment. So I've cloned it, and then I can go up here to Open Workspace, select crack 3, and then I get a separate window that has just the files for this project in it without any of the clutter of the other files in there. So let's look at crack.c. So the first thing you might want to do is define a struct called entry that holds both the plain text password and a hash. And there's a couple of ways you can do this. The choice is yours. You can do struct entry and then have 2 strings in there for the plain text password and its hash. There's a define somewhere at the top that basically says 50 characters is long enough to hold any password in this file. So you can do it as a structure containing 2 hashes, 2 strings, one of them 50 characters long and one of them 33 characters long, to hold the plain text password and its hash. And then another way to do it would be struct entry. Instead of 2 strings, hold 2 pointers to strings. So what's the difference between the 2 of them? Well, in the first one, obviously, the strings go along with the struct. So if you have an array of structs, then inside of each element, you have the plain text password and its hash stored in the element itself. That means each one of these elements is going to use up roughly 83 bytes of memory. Now, there's no way to get away from that. You're going to use up that memory regardless of which one of these you use. But the downside, and this is a very slight downside to this, is that when you sort that array, you're going to have to move all 83 bytes around. So there's going to be some string copies going on in order to swap these values around. So it's just a little extra work to do while you are sorting the array. Actually, you don't have to do any string copies. You just pass the array into qsort, and remember, you pass it the size of each element, and it handles copying the bytes back and forth for you. It's just got extra work to do because there's 83 bytes, give or take a little bit, to copy around. Whereas in the other structure, you don't have the plain text password and the hash stored in each element. Instead, you just have pointers stored there. And then each one of those points to the actual values, the actual strings. So it's a more complex data structure. But when you sort the array, all you have to do is just move these elements around that are only 16 bytes apiece to 64-bit pointers. And so it's less work for qsort to do. The strings themselves just stay wherever they are in memory, and you're just sorting the elements of the array around. But nevertheless, both of these will work, and it's your choice as to which one you want to do. So next, there is a function called read dictionary. You pass it a file name that contains the name of the dictionary, and then a pointer to the size variable. And then you need to fill in this code. And the code here is going to be very similar to the load dictionary function you wrote for the previous assignment. The previous assignment was really just to get you ready to do this one. And so it's going to open the file, read in the dictionary file, hash each one of the passwords as it goes, store them into that structure, and then build the array of structs. You may want to use the growing array technique that we talked about last time, so that you can grow the array as the words are being read in. Alternatively, you could read them all in and then count the number of words and then allocate the array in one fell swoop. That was another example we did, again, about 2 weeks ago. So again, your choice how you want to do that. And then it's going to return the array of struct entries. So it'll return the array, and it also needs to set the size. Here I set the size to 0 just so it'll compile, but you need to change this to be something more appropriate. So that'll read in the dictionary and pre-hash all the passwords. And then finally we've got main down here. Main just simply calls read dictionary. You're going to have to change these two nulls to be something more appropriate. So remember, the first parameter to read dictionary is the file name, and the second parameter is the length of the array. And then it hands back the array of dictionary entries. Then you're going to call qsort. Here you'll also need to change these parameters. And then right here, I have a little test example of calling bsearch, binary search. Eventually you should comment this out, but this is just here to make sure that things are working. If your qsort has worked and your read dictionary has worked, then you should be able to do a binary search for this particular string, and it'll return the rocku entry. So here's an example. You're going to pass in the string, pass in the dictionary. You need to change these numbers, and the null over here. You need to change these. So once you're sure that that is working, you can then write the rest of the program, which simply opens the hash file for reading. And then for each hash, search it in the dictionary using binary search. And if you find it, print out the hash along with the plaintext password. And then you should only need one loop to do this. Okay, so that's the program in a nutshell. So this really kind of puts together a lot of the concepts that we've been learning over the past couple of weeks. We've got structures, we've got string manipulation, binary search, quick sort, expandable arrays, arrays of structures, file reading and writing, pointers, arrays, right? Like pretty much everything is in here. And I hope over the last couple of weeks, I have given you enough of the pieces, not in this, obviously, the exact format, but enough of the pieces that you can put together those concepts and build this program. Try not to tackle the whole program at once. This is like my primary advice to anyone who's tackling a large project is it really can be difficult to kind of get your head around the whole thing. And maybe until you get your mind wrapped around the entire problem, you don't really fully understand what's going on. So it may take you a couple of kind of starts to get going. Like start it, see how far you can get, and then maybe you realize that was not quite the correct approach. Start again, and and do it again until you can see how all the pieces fit together. So, like, what does that mean? It means maybe, work on read dictionary first. Try to take what we did out of the previous assignment and drop it into here. It'll have to be changed a little bit. You won't be able to just copy and paste, but more or less you'll be able to put it in. And then see if you can sort it. Maybe after reading in the dictionary, insert some lines here to print out the dictionary and just make sure it's all there. I think there's a little bit of a mindset among some beginning programmers, or not say beginning, but you know what I mean, like, haven't done a whole lot of programming. When they're given this template code, they find the places to fill in and then don't do anything else with it. But you are, of course, free to insert your own lines here if you need it for debugging, if you need that just to build your confidence that things are working correctly. Go ahead and insert some prints in there. Go ahead and insert some loops to print things out. And I think that will help a lot to kind of let you know that things are going well, that you're making progress toward the solution. So my suggestion there was, try to get read dictionary work and then insert a line here, or a line or two here at line 39, to just print out the contents of the array and make sure it's all there. And when I say make sure it's all there, go back and compare it to the Rocky file. Make sure all those entries are there. Make sure the last one is there, Alexandra. Make sure the first one is there, 1, 2, 3, 4, 5, 6. It can be kind of easy sometimes to not forget, but to write your code in such a way that like the first one is omitted or the last one is omitted. Just make sure they're all there. Once you got read dictionary working, work on the qsort. And then, again, maybe after doing the qsort, print it out. Just make sure it's sorted. Try to do the binary search. Make sure something is found, and learn how to take the entry that was found and print out the individual pieces that are within it. So again, my advice there is not try to tackle the whole program at once, but try to write it incrementally. Try to write a little piece and convince yourself that that little piece is making progress towards the final program. Anybody else who's watching or listening have any little nuggets of advice for people to tackle a program of this size? I'm curious, what's been...
Yeah, for me personally, the small chunks is very important.
Yeah, doing it in small pieces.
I'll always make sure I have the input being read and coming in correctly before I do anything else. It doesn't make any, it doesn't help to work on your algorithms if your input's not even correct.
Yeah.
So
there's a phrase, like garbage in, garbage out.
Right.
Right. So if the values coming into your program are not correct, then there's no way the output's going to be correct. So good advice there. Just make sure the inputs are coming in correctly. So my YouTube, Calslaw says, iterative programming is the best thing you can learn when starting out. I guess it's the same advice, basically. Break it down into small chunks. Break it down into small chunks and then check that each chunk is doing what it's supposed to do. And you don't have to work it. You don't necessarily have to do it from top to bottom. You know, there's basically only, what, 1, 2, kind of 3 things to do for this program. But, you know, could you maybe tackle opening the hash file for reading and then printing out each of the hashes before you do anything else? I mean, you probably could. You might have to go back and rework that later on, but at least that would like make progress. So even if you don't know what to do with read dictionary or with qsort, can you open the hash file for reading and just print out everything in the file? So kind of just start somewhere. Find a place to start and just start working at it. Start chipping away at it. And keep in mind that you may have to rework some portions of the program as you learn more and more about how it's supposed to behave. Okay, any other questions on this? So again, you can look at this picture. These are 2 possible ways to organize that entry structure. Either it's a structure of 2 strings, so the whole structure is about 83 bytes long, or it's just a structure of 2 pointers, and so the entry structure is about 16 bytes long. So the advantage of the top one over here is it's probably easier to build this structure. At the expense of sorting and searching is probably a little bit slower because there's just more stuff to look through. The bottom one here is probably maybe a little bit more difficult to build, although probably not too much more difficult. The advantage here is that sorting is probably going to be faster because each of these entries that need to be swapped has only 16 bytes in them as opposed to 83. The strings themselves, the hashes and the plaintext passwords, those once allocated don't move around. I guess the other thing that I've learned over the years is that when I draw a picture like this, I consider each one of these boxes as kind of like there should be a malloc for each one of those. So if I see this box here floating around, I know there needs to be a malloc for that one. And if I see this one, I know there's needs to be a malloc for that one. So already I can see there ought to be at least 2 mallocs in my program. Probably a 3rd one for this one here. And then since this is a kind of a repeating structure, those are going to go inside loops. And then also each one of these arrows means that there's going to be an assignment statement that ties this pointer to this chunk of memory. So it's kind of like a to-do list. You know, make sure there's a malloc for this one, make sure there's an assignment statement, make sure there's a malloc for this thing, make sure there's an assignment statement. And you can kind of just go through the data structure and just check off each one of those boxes and make sure you've got the line of code that corresponds to that. That was another one of the aha moments for me when I was in college. I was in a data structures course, and we were allowed to work with partners on this particularly large program. And we had all been just like hacking away at it for a couple of days and not making a whole lot of progress. And finally, my partner, he stood up and he said, let me just draw this whole thing out, right? Now that we kind of see what the pieces are, let me just draw it out. So he erased the chalkboard or the whiteboard in the computer lab and started drawing all these boxes. And he just said, here's what it's supposed to look like when it's done. So let's just go through the code and make sure that each one of these boxes has a malloc and each one of these arrows has an assignment statement on it. And sure enough, you know, we found places where there weren't connections being made between the boxes. But it really kind of illustrated to me that once you know what the data structure is supposed to look like, he said the code almost writes itself. And I was just astounded that after we drew that picture and then wrote the code to match the picture, it worked. I mean, it was just like this big old grin on our faces, like, oh my gosh, it actually worked. And then this is a related but not related story. There was another fellow in my class, and he was like this programming genius. I mean, he was just, you know, as far as his programming maturity, he was way ahead of the rest of us. And so this is kind of a funny story, is we were writing the data structures in C++. And at the time, this was the early 90s, C++ was a brand new language. The compiler for C++ wasn't a native C++ compiler. Instead, it was a compiler that just took your C++ program, translated it into an equivalent C program, and then ran it through the C compiler. And it was new, right? And it was only maybe a couple of years old. And so he was writing this program that had to build this data structure and then basically sort it and then display the results. Not too much different than what we've got over here. And so he would write the code, and then he'd go on the command line and run the program. He would type in, like, you know, sort, and then the name of the file that was the input file. And like, nothing happened. Actually, to tell the story correctly, he didn't even type in sort in the name of the file. He just typed in sort, and the name of the file was built into the program. He just typed in sort, and it would just sit there. And he goes, huh, there must be some bug in my program. So he'd go back and look at the source code. He'd go, oh, there's a bug. He'd fix it, run it again. He'd type in sort, and then nothing would happen. He goes, well, it must be another bug in the program. So he'd go through the code, fix another bug, run it again, same effect. And then finally he realized he wasn't running his program. He was running the built-in sort program that comes with the shell. And if you don't give it the name of an input file, it just sits there waiting for you to type something in. And he had chalked all this up to bugs in his program and bugs in the C++ compiler. So when he finally realized that he was not running his program, he was running the built-in program, he changed the name of the program to be something else and then ran it, and it worked perfectly. And the rest of us in the computer lab were like, oh my goodness, he just debugged a program that he never ran. He never actually ran his program, but he debugged it successfully. He found bugs, fixed them, and then when he finally ran it for the first time, it worked. He was also astounded himself. He was like, what? How did I do that? But we all knew he was a pretty good programmer at the time. Let's see, Calsala says, I don't know if you said something like this, but write comments with how you want your functions to operate. Break it down into steps and describe generally all the steps you'll need to take. I think this is just a huge piece of good advice, and this is a skill that you need to learn over time, just how to take a problem, break it down into small, manageable pieces, and then test each one of those pieces, make sure they work, kind of like what Chris said, is like write a little piece and then write some little debugging code just to make sure it's working, and then move on to the next piece and then figure out how to assemble all those pieces together. So if there are no more questions, I want to go on and do something else. This is kind of related, but not related, just because I wanted to fill up the time for today. And that was when we started introducing this idea of doing binary search. The prerequisite for that was to sort the array. And we wrote a bubble sort program to do that. We used bubble sort to sort a whole bunch of numbers into order, and then we were able to use binary search. And bubble sort worked fine as long as the array was pretty small, but if the array had gotten bigger, bubble sort would have taken a long time. And I think I mentioned at the time that I coded this up on an older computer, and it was going to take something like 33 hours for it to sort an array with 2,000 entries in it, which even today's computer could handle pretty quickly. And then I showed qsort about how much quicker that was compared to bubble sorts, particularly with an array with like 1 million entries in it. But I never actually showed you how quicksort worked. Kind of described it as being a recursive algorithm that successively breaks the array into half and then into half again and half again. But that was as far as I get. And you can find lots of videos about how qsort works, but I thought maybe it might be a good idea to just code it up and see if we can get quicksort to work instead of just relying on the built-in one. So if you haven't seen how quicksort works, here's generally how it works. First, you have an array. Let's do numbers. Numbers are easy. Let's do like 10, 7, 8, 9, 2, 1, 6. So let's say we want to sort this array into order. It should go 1, 2, 6, 7, 8, 9, 10, obviously. And so what you do is you got your array, and you could either randomly pick one of the elements, or you could just pick the one on the low end, or one on the high end, or one in the middle. But you just pick any one of the elements to be what's called the pivot. So in the implementation that I'm going to show you, they pick the rightmost element to be the pivot. It really doesn't matter which one you pick. You can pick it randomly. You can pick the first one, the last one, the one in the middle. It doesn't matter which one you pick. But in this case, I'm going to pick 6 to be the pivot. And then what you do is you start moving this pivot around and basically reorganizing the elements so that everything that's less than the pivot goes to the left of it, and everything that's greater than the pivot goes to the right of it. You don't worry about sorting them, you're just moving them. So everything that's less than 6 goes to the left of 6, and everything that's greater than 6 goes to the right of 6. This is called the partitioning phase. You're going to partition the array into 2 halves. So let's see. We're looking at this here. Everything that is less than 6 will go to the left of 6. So 2 is less than 6, and 1 is less than 6. And then here's the pivot. And then everything that's greater goes on the other side. 10, 7, 8, 9. Okay, I didn't worry about sorting any of those numbers. I just simply moved them. But now what we can say is that the pivot number is in the correct spot. This is where it should eventually go. It's going to be in that 3rd spot. And then what you do is then sort the left half and then sort the right half using quicksort again, just on smaller arrays. So here's the left half. We'll pick the pivot, which will be the rightmost number. And then we'll move everything that's less than 1 to the left-hand side, and everything that's greater than 1 to the right-hand side. So we'll end up with 1, 2, 6, and then 10, 7, 8, and 9. And then do the same thing to the right-hand side. Pick your pivot, move everything that's less than 9 to the left, everything that's greater than 9 to the right. So we'll end up with 1, 2, 6, and then let's see, 7, 8, 9, 10. So at this point, 2 is in the right spot, 6 is in the right spot, and 9 is in the right spot, because those were our 3 pivot numbers. And then do it again. So sort this. Now, if you have an array with only 1 element in it, it's already sorted. And so that's now in the right spot. Then do it to this array. Pick the pivot, move everything around, and then you'll find, of course, that this is already sorted. So now this is in the right spot, this is in the right spot, and then this is in the right spot. And basically, in only 4 passes, we sorted the whole thing. So here's an algorithm. Start with quicksort. We've got our array A. P is the leftmost element that we're sorting, and R is the rightmost element that we're sorting. So those are the indexes. And so basically when you call quicksort the first time, you give this a 0, and R is the index of the highest element. Then it says if P is less than R, so in other words, if the chunk of the array that we're doing is more than 1, the length of the array is more than 1, then partition, and then sort the left side, and then sort the right side. And that's the whole thing. And then here's partition. So partition is going to, let's see, this is our pivot, X, I, and J are the left and rightmost indexes. And then this section here is just moving that pivot around. So it's going to find an element that is less than the pivot, and then find the element that's greater than the pivot, and then it starts swapping things around. So let's see if we can, I'm going to rewrite this in something that uses maybe, well, let's try this out. I'll go back over here. Okay, so let's make our array, int array, and let's put in our numbers. Let's do, I guess we'll do 7 numbers to begin with. Let's do like 9, 5, -2, 7, 6, 1, 0. That's it, 7 numbers. And then we're going to call quicksort. We'll pass in the array, the lowest index number, and the highest index number, which is length minus 1. So the highest index is 6. And then print it out. Okay, so that's our call to quicksort, and then print it out. All right, so let's do quicksort. We're going to be given an array. Let's call it A. We're going to give the low index number. Let's just call it low. And the highest index number, we'll call it high. And then if we look at this, we call if P is less than R, so if low is less than high, if low is less than high, then call partition, and what we get back is Q, which is the index of the pivot element that we used. So let's go int pivot index equals partition. We'll pass in A, P and R, which is low and high. And then we'll call quicksort on each of the halves. So we'll pass in A, and then the low is going to be low, and the high will be pivot index minus 1. And let me just check to make sure that was correct. Oh, P and Q. So don't subtract 1. And then quicksort A, and the low in this case will be pivot index plus 1. And the high will be whatever the high was. So that's basically the entire algorithm. Call partition on the chunk of the array that you're looking at, and then quicksort each one of those 2 halves. But let's do partition. So we're given our array, P and R, which again we'll call low and high. Okay, so X equals A sub P. So that is our pivot value. And then I equals P minus 1 and J equals R plus 1. P is low, is that right? Low. And R is high. Okay, while true, so while 1, repeat, J equals J minus 1 until A sub J is less than X. All right, so that'll be like a do while. Oops, wrong tab. Do J minus minus while. Oh, it's until. So repeat until. Actually, I guess I'll just do it like this. While. I need to reverse. This is until, but we're doing a while. So until means drop out of the loop when this happens. And while means continue this loop while this happens. So we need to flip this around. So this becomes A sub J is greater than X. While A sub J is greater than X. X is our pivot value. J minus minus. And then while, this is the other one down here, while A sub I is less than X, then what is this? Increment I. Okay, and then if I is less than J, swap A sub I and A sub J. If I is less than J, is that what it said? Yeah, if I is less than J, int temp equals A sub I. A sub I is equal to A sub J. A sub J equal temp. Else return J. Okay, and that should be the whole thing. Okay, so let's take a look here again. So the partition is handed the array and the low and the high index values of the section of the array that it's working on. Initially, it's going to be the entire array. If low is less than high, so basically if there's at least one element to sort, then partition the array, giving back the pivot index, and then a quick sort the low side, and then quick sort the high side. The partition function takes in the array and the section of the array we're working on, picks a pivot value, in this case just the one on the high end, and then two counters that start on either end of the array, and then those counters start moving towards the middle. And then once they find values that are either less than or greater than the pivot, swap that thing around so the pivot moves into the right position. Keep doing that. Keep moving in until we're able to not move the pivot anymore. And then we know that everything that is less than the pivot is on the right side, on the left side, and everything that's greater than the pivot is on the left side. You know what I'm saying, right? Let's move things around. And then when it's unable to move the pivot anymore, then return the index of the pivot. Okay, let's give this a shot. Here, let's save this. Oh, what's going on? What did I call this? There it is, qsort.c. Oh, I put that into the crack3 directory. Let me move that out. All right, moment of truth. Uh-oh, we have an infinite loop. What happened? Now we just need to double check that we did all this correctly. So if low is less than high, if P is less than R, pivot index equals partition AP and R, AP and R, and then quick sort A, and then P, oh, P and Q, did I do that right? Yep, P and Q, and then quick sort A, pivot index plus 1 and R. That looks okay. So let's go and look at partition. Pivot value, because oh, this is P here. This is the low. Aha. So that could be our problem. I don't think so, but that could be our problem.
It's like on lines 8 and 9. If I is low -1, then isn't that -1? So we're trying to access an element outside of the array.
Oh, I see. So what actually happens first here is the first thing it does is it increments I again. You see that? So you're right. Right. Initially this becomes negative, but then the first thing it does is it increments it.
But in our code, it increments it after doing the while check.
Yeah, so I need to make this a do. Do J minus. Wow. Is this better? Ah, it's still stuck. I wonder where it's getting stuck. Well, a sub j is greater than pivot value. Good. Do I plus plus while a sub I is less than x. Yep. If I is less than j, swap a sub I and a sub j. If I is less than j, I, j temp, else return j. Well, that's interesting. So where could it be getting stuck? How would we figure out where it's getting stuck? I think what I'm going to do is every time it calls qsort, I'm going to print something out. Let's print out Q. So hopefully we'll see more than one Q appear. Oh, nothing appears. Oh, let's print this as standard error so that I make sure it's getting flushed right away. Nope, nothing appears. Okay, interesting. Any ideas? It never prints out this Q. Let's put a new line on there just to make sure. Nothing. Let's just print this out here. Wait a minute. It doesn't even print out sorting. This seems weird. It's almost like I'm not even running my program.
So if it was me at this point, I would comment out the first two methods and comment out the calls in main and just see, okay, can I get to print something out, and then start adding pieces back in.
Why isn't it printing anything out? Let's see, I'm in my home. Oh, I see why. So remember I moved the qsort program into the proper directory? But every time I save this, I'm still saving it in the crack2 directory. So I'm actually compiling and running the wrong program. So let's close this. Let's see. So this is the one here that's correct. I'm gonna copy this and just make sure. And then let's go down to the correct one, which is this one. Paste in my latest code. Okay, there we go. Now it prints out sorting, and it's still not sorted because I commented out qsort here. All right, now we're in business. All right, Q. So every time it calls qsort, it prints out Q. All right, it's in order. -2, 0, 1, 5, 6, 7, 9. So that's qsort there in a nutshell. Sorry about the compilation problems, but that happens. But nevertheless, it does seem to be working. So partition the array, and then qsort the left-hand side and qsort the right-hand side. And then here's the partition function. Now there's more than one way to do this partition. This is just the source code or the pseudocode that I found on one website. Here's another one. The qsort is pretty much the same, but the partitions are a little bit different. Nevertheless, they both will work. So any questions about that? Okay, so now that we've got that straightened out, let me go and delete this other qsort that we don't need anymore. No questions there? What's the best way to debug recursion? Well, I've done it with print statements. And what I've also done is, see, notice that this one here is printing out a whole bunch of Qs every time quicksort is being called. And I guess sometimes what I'm interested in knowing is every time I do a recursive call, I want to know, is that the result of kind of like a first level call, or is that a second level call, or a third level? In other words, how deep into the recursion are we going? And so instead of just printing out Q, why don't we have maybe a global variable called depth? And we'll start it out at 0. And every time we call quicksort as a result of a recursive call, we'll increase depth. And every time we return from quicksort, we'll decrease the depth. So like right here, right before we call quicksort, we'll say depth plus plus. Same thing here, depth plus plus. And then every time we return from quicksort, which is down here, we'll say depth minus minus. So when we call quicksort, we increase the depth just before we call it, and just before we return from quicksort, we decrease the depth. And then right here, we'll have it print out the depth. So now we get a series of numbers that shows initially our depth is 0, so that was our first call to quicksort, and we should only see 1 0 on there. But we should see a couple of 1s because we've split the array into 2 halves. So here's a call to 1, and then here's the 2 left and right halves of the left-hand side. And then there's a 3 and a couple of 4s and a 3 again and a 4. We even get down to a depth of 5, and that's because our array that we're using is really not very well balanced, right? You know, one of the smallest elements is all the way over there to the right-hand side. So let's see if we make this array bigger. Let's increase the length. Let's go up to, let's say, 100. So int array length. Actually, let's use malloc. Int pointer array equals malloc length times size of int. And then we'll just fill it with a bunch of random numbers. And then, of course, we'll need to initialize this srandom with the current time. and which means I need to bring in a couple of includes to get that to work. So there's my sorted array, but here you can see all these calls to quicksort. So we start with our initial depth of 0, and then we start descending down. 1, 2, 3, 4, 5, 5, 6, 7, 8, 8, 7, 8. So it's going down, 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 and kind of hovering around. We can see we get down to a depth of 12. Actually, a depth of 15. Now, if the array was truly random and nicely balanced, where the random numbers were all scattered around evenly, then we would expect for an array with 100 elements in it that we should have a depth of no more than the log base 2 of 100, which is about 7 or 8. But because the numbers are not well balanced and our pivots aren't being chosen randomly, then we might end up with a depth that's a little bit more. But on average, it should be about 8 or so. If we ran this program again, we'll see a different depth. And here it seems to be maxing out at about 12 or 13. So that's one way to help with debugging the recursion, is just to make sure that the depths aren't going crazy, and that in fact it's going down and coming up and going down and coming up. So I'm maintaining this global variable called depth, and then every time I call the recursive function, I increase the depth, and every time I return from the recursive function, I decrease the depth. And then the other thing you can do, now that you have the depths being printed out and you know that calls are being called, now you can put in your print statements and you know kind of at what level these prints are happening. So you know whether the print statements are happening at top level, bottom level. In fact, every time maybe a quicksort, we could print out %d, low, comma, high. And so now what we got here, if we can scroll all the way up, is initially depth 0 is doing it on the whole array. And then at depth 1, this is the left-hand side. So from 0 to 83, and then from 0 to 64, and then 0 to 7, 0 to 4, 0 to 3, and then finally 0 to 0. So we've sorted the entire left-hand side. And then 1 to 3, 1 to 2, 1 to 1, 2 to 2, 3 to 3, 4 to 4. So this is kind of neat, showing how it's sorting the whole left-hand side up, and then sorting the whole right-hand side. So where's the other depth 1? That'll be the switching point, where it goes from the left-hand side to the right-hand side. I'm scrolling up. I'm looking for a 1 in the left-hand column. So I'm looking for the partner to this one. I'm just obviously scrolling past it, and I'm not seeing it. There it is. There's the point at which it switches from the left-hand side of the big array to the right-hand side of the big array. So I'll tell you where this started coming up in some of my voluminous free time of hobbies over here. Is you know the game Wordle, where you have to guess the 5-letter word in 6 guesses or less. And I thought, well, there's a ton of implementations of Wordle. How about getting Wordle to work on one of these old computers back here? I mean, just for fun, right? Not because I have any practical use for it, but just for fun. And so I started breaking down what are the steps needed to play Wordle. So the first step is now in the regular Wordle game, there's only 1 word per day that's chosen. But I want to be able to play this like over and over again. So basically the first step is pick a random word to be the target word that you're trying to guess. Well, where do you get those words from? Well, you can download a list of all the Wordle words, and there's about 2,300 of them, 2,300 of them. And so those are all the words that the game knows about. There's about 2,300 5-letter words. And you just pick one of those at random. So on one of these old computers, you have some severe limitations. You have only 64 kilobytes of memory. And let's see, 2,300 words times 5 letters each is going to be 11.5 kilobytes. So just an array, and now that's actually 2,300 times 6, because a string is the 5 letters plus 1 additional character. So it's 13.8 kilobytes to hold the array of strings. And we don't have the whole 64 kilobytes. We have only about 34 kilobytes, because you need, I think, 8 kilobytes for the ROM on the system, and about 10 kilobytes for the basic language interpreter, plus some other pages set aside for chunks of memory set aside. Your programs can only occupy about 34, 35 kilobytes of the 64. And already your array is using up 13 of the 30 or so that you needed, which doesn't leave a whole lot for the gameplay itself. I mean, you might be able to do the whole thing in the 35 kilobytes or so, but maybe not. And so you could read that entire array into memory and then pick one at random. So that's the first step. The second step is to ask the user for input, and then start doing the process of seeing which letters are in the right place, which letters are in the word but in the wrong place, and which letters aren't in the word at all. That's actually fairly easy to do. You can do a few loops through the string and just first see which letters are in the right place, and then see which letters are in the word but in the wrong place, and then finally which letters are not in there at all. Those are just a few loops to do that. But before you do that, you need to make sure that what the user typed in is a valid word or not. Is it one of the 2,300 words that it knows about? So here you got to turn attention back to that array and search through that array and see whether the word that they typed in is in that array to begin with. Now, I actually typed that in to one of these old computers, and it would take about 5 to 10 seconds to find that word. It's mind-boggling to us, right, to search through an array of 2,000 strings and have it not take just a fraction of a second. But this actually took about 5 seconds to search through that array to find if that string was there. And I thought that might be an unacceptably long time between the user typing in their word and when it told you whether it was a valid word or not. Just from a user interaction point of view, waiting 5 seconds for even just a check to see if your input is valid might be too long. So how can we speed that up? Well, one thing to do would be to take that array of strings and sort it so that we can do a binary search on it. So I wrote a program to do that, and actually I implemented qsort. And I think I told you maybe about that a couple weeks ago. I implemented qsort, but we don't have recursion on this basic programming language, and we don't have local variables. So I kind of had to cobble it together myself. I used arrays to hold stacks of variables. So anytime I needed a local variable instead of quicksort, I had an array to hold all the variables. So I had a low array, a high array, a pivot index array, a pivot value array, and then I would have this depth counter that every time I called quicksort, I would increase the depth, and every time I returned, I would decrease the depth. And so it was building up stacks of variables, kind of like a call stack in C, where you got stack frames holding all your local variables that rolls and unrolls. So basically implementing my own version of recursion, but without the benefit of having local variables, or actually the benefit of having a call stack at all. So I got that to work, and quick sorting the array takes about 3 or 4 minutes. So obviously you wouldn't read in the array of strings and then quick sort it before the game began. That would just take too long. What you would do instead is read in the array of words, quick sort it, and then write that out to a file. So the next time you run the program, you just read the file in and it's already sorted. So I could read the array in and then do a quick sort on it. Not a quick sort, a binary search on it. I haven't done that yet, but I imagine it's going to be fairly quick, because searching through an array of 2,000 words for the one you're looking for is not going to require searching through all 2,300. It's only going to be required searching through about 12 or 13 of them. Because when you break it in half and break it in half and half and half and half, you should be able to look at no more than about 13 or 14 words before you find the one you're looking for. I think that'll go much faster, like a whole lot faster, like maybe less than a second, to figure out if the word is the one you want or not. But we're back to another problem, which is if I store that array in memory, it's going to use up a huge amount of memory. It's going to use up almost half of my available memory. And will that be enough to implement the rest of the game? I'm not sure. So what can I do now? How can I have this giant array I need to search through, but conserve as much memory as possible? So my idea was to store the file on disk and then search it. Here's the other problem, is we're going to read in this array with 2,300 words in it, but if we only play the game once, we're only going to have to look at about 13 of them. Right, so we're going to read in this giant list of words, and we're only going to need a very small fraction of them as we play the game. Most of them we will never encounter. So why read it into the first place? Why not just leave it on disk and then search the file? So the user types in a word, like skunk or something like that, and then do a binary search on the file itself. Start in the middle, read in the word that's there, and then go to either the left or the right. Because every word is exactly the same length, every word is 6 characters long, 5 plus Terminator character, you can do a binary search on it. You can calculate what position you should move to the file. Right? So we know there's 2,300 words. Each one is 6 characters long. So we should go to position like it's 13,800, divide that by 2, and that should give you the position to move to in the file to read the first word in the one that's in the middle. And then from there, you can calculate the positions to move the head around in the file to find the word you're looking for. So then the question is accessing a file slower or faster than reading in the entire array? And that's an experiment I want to do. Is searching the file slower than reading the whole array into memory and searching that? Nanya on YouTube says you can more or less do your binary search with a file pointer, perhaps. Exactly, that's what I wanted to get to. So that's an experiment I want to do. Is what is like the if I do a binary search on a file, is that going to be reasonably fast enough for my program? Or is there some hybrid approach I can take where maybe I could hold, like, I don't know, half the file in memory, do a binary search on that, and then do the very last step on the file itself to find the very last word. I don't know, something like that. So when you're doing a binary search on a file, you got all these words. Actually, I'm just going to do an array with a bunch of things. Pretend there's numbers or words in here. So you find the middle one, and then you calculate whether it goes to the left or the right. And then you find the middle one, calculate where it goes to the left or the right. Find the middle one, left or right, find the middle one. And so you kind of end up jumping all over the place. And for one of these old floppy disk drives, moving the head back and forth takes a fair amount of time. You got to start at the beginning of the file, go to the middle of the file, and then from there go to the middle, and then from there go to the middle, and then from there go to the middle. You're moving this read to write head back and forth through this file. That could actually take some time. And when you want to search this array using binary search, the first step is always going to be that middle element, right? It's always going to be that one. And the second one is always going to be either that one or that one. You know what I'm saying? And the third one is always going to be that one, that one, that one, that one, or that one, right? So there's always going to be the middle element for the first one, one of two quarter of the way through elements for the second one, one of 8 ones for the third one. Those are always going to be the same. So we've got this double whammy of a problem, which is one, moving the read-write head back and forth through the file is probably going to be slow, because we're going to have to move it forward, read one little word out of that, and then move it over here, read one little word, move it over here, read one little word, move it over here, read one little word, right? That's going to take some time. And the other problem is, what I say? Oh, when we do the binary search, it's always going to be the same first word, and one of 2 same second words, and one of 4 same third words. So here's something we could do. Instead of arranging the file from low to high, we'll arrange it in the binary search pattern, where the middle element is the first one. Okay? And then the middle elements out of the left and right half are the second and third elements in this new file. And then the 4 elements that could be our third guesses are these, and there aren't really going to be any gaps between them. I'm just showing the gaps to illustrate what's going on here. And then there'll be another set of 8 here. So when I do my binary search, I start at the first thing in the file, and that's going to be my middle element. And then whether I go left or right determines whether I read this one or this one. So I'm always going to pick one element out of each one of these groupings, right? And the third guess is going to be, one of these 4. And the fourth one is going to be one of these 8. And what the advantage here is that I'm always moving forward through the file. I'm not moving back and forth. So basically, because the files are buffered, I'm not just going to read in this one. I'm actually going to read in this chunk into memory. And then it becomes really fast to search through it. And then I'll read in the next chunk. It'll be fast to search through that. So I'm doing a binary search, but not by moving the head back and forth, by just moving it forward. And so it should be fairly easy to calculate. Do I do the left one here or the right hand one? Do I do the first, second, third, or fourth one here? Do I do the first, second, third, fourth, fifth, sixth, seventh, or eighth one I had here? Should be easy to calculate that. Yeah, so people on YouTube are like, yes, so this way, the read-write head is always moving forward to the file. You're never going to go backwards. And it only has to go forward a few indexes each time. So the idea here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's a total of 14 elements in here. So the middle element would be, I guess, number 6. And then this one here would be 3. And I guess 9. And then this one over here would be 1. And this one would be 4. I think, so basically the way you calculate it is, you've got your middle element, which is 6 here. This one over here is always going to be this number divided by 2. Whatever this number is, this one is going to be that number divided by 2. And then this number over here is going to be this number, I think, plus this number. So that's why I came up with a 9 here. And then this element here will be this one divided by 2. And this one here will be this number plus this number, which is 4. And then this one here will be this one divided by 2. And is that right? And this one over here will be this number plus this number. So you can very easily calculate all the indexes of each one of these little chunks. So this is basically linearizing the binary tree so that the root is at the front and the leaves are towards the back. So that's another experiment I want to do, is first let's try just doing binary search by moving the head back and forth, and then let's try rearranging the files so that the file is from the root at the front, leaves toward the back, and that way you're always reading forward through the file. So those are some experiments I want to do. And there's actually a third experiment I want to do, which is a little harder to describe, but it basically involves using hashing, and then using the hash value as an index into an array. And using a hash value, we should be able to reduce the number of elements we look at by quite a bit. So that would be called like a hash table. So the hash table would waste some space. There would be some elements of the array that aren't filled in, but hopefully most of them will be filled in, and we only have to look at a few of them to find the value we're looking for. Ideally, only one. Oh, of course I'll show my results. In fact, I was thinking about doing it this summer. Once school lets out, once classes let out, I'm hoping I'll have some time to do some like live streams where I'm just coding up these programs on my old 8-bit computers, and you can watch, and we'll do these experiments and see them happen in real time. You know, I'll start with doing binary search and show how unbelievably slow that is, and then we'll just switch it over to qsort. And I actually implemented, like I said, I implemented this qsort algorithm. Oops, this one. And it worked pretty well. And then from there, try all these experiments with organizing the data on disk and see which one ends up being faster. And that's all just so we can search through the array of words and figure out if the user typed in a word that's valid or not. The rest of it, during the rest of the game part that you see, which is the green and the yellow, that's the easy part. It's searching that array that I think is going to be interesting and more difficult. All right, so it's about 11 o'clock. On Wednesday, we'll come back and we'll start in on networking. So we'll teach you a little bit about the terminology, you know, how data is sent and received. You'll want to come back for that because my concept there is I will also hook up some, you know, actual communication hardware. We'll hook up some diagnostic equipment to it. You can see some of it back over. I'm doing this backwards right here. We'll hook up my oscilloscope to some equipment that can send data back and forth, and we'll see the actual waveform of bits going down the wire. And so you'll get some idea about how data is actually transmitted in real life from one piece of equipment to another piece of equipment. And so we'll take a look at that, and then we'll start talking about some of the concepts of computer networking, and that'll introduce the very last programs we're doing, in which we're sending and receiving data to computers that are out there on the internet, and you're going to do something with that data. So I haven't decided yet what that is, but who knows? Maybe we can play Wordle or something like that. You send your choice out, and then it comes back and it tells you whether or not that was a good guess or not. That's actually an interesting idea. Yeah, internet version of Wordle. So that's it for today. We reached 11 o'clock. Any last questions before we go? Okie doke. Well, have a great day, everyone.
Thank you. You too. All right.
Hope that was interesting.
It was very good.
All right. Take care.
Bye.
Right, bye-bye. And then the folks who are on YouTube, thanks again for watching. Yeah, I've been kind of like working on this binary search problem for a couple of weeks now. I can only spend, an hour every couple of days on it. So far I've got it. It's sorting the words. I've got it writing the file out with the words in order. And my next thing to tackle is doing the binary search on the file. See how that comes out. And then rearranging the files so that they start at the root and go towards the leaves. I haven't yet figured out how I'm going to do that, but I'll figure it out. I mean, how am I going to actually reorganize or work my way through the binary tree so that it writes the data out in that order? But between now and Thursday, I need to set up the oscilloscope and some equipment to send and receive the data so we can take a look at it. All right, folks. Have a good day. And I will see you on Thursday or on Wednesday if you want to start learning more about finite state machines and non-deterministic and deterministic finite state automatons. Thank you, Lord Melbury and None Your Business and Akash, and who else was on here? Yannick, Kauslaw, and everyone else who was watching. Thanks for being in on the stream and giving your input. It's always good to see you, and I will see you next time. Have a good day. Bye-bye.